Hello? Hello?
Yeah, we can hear you.
Okay.
Hey, you will.
All right. Well, I'm sharing my screen. Let me know at any time if you can't hear or see the slides, but the slides are also on the Google Classroom as they have been previously. So you're free to look at them there. Hopefully it is. I see people on the slides, so I'm guessing they're there. Welcome back. This is week 3 of 4, so we're almost there. Just to give you a reminder, this is kind of the original overall plan for the 4 weeks. I'm going to go slightly in a different way with this class for week 3 specifically. I'll start off just by reviewing a bit of what we talked about, concepts in dynamics, and specifically about torque and RPM. I did realize between last class and this class that there are a few things that I could have maybe explained more explicitly when it comes to like torque and gears and such, which I saw when I looked at like some of the like submissions for the homework. So we'll do that, and then I'll talk about CAD, computer design, specifically using Onshape. So I brought this up last week. Hopefully most of you have had some experience with Onshape, or at least have made an account before, but I will briefly go over that as well. So if you haven't, there will be a time to do that. And I'll introduce a concept called statics, which will lead into the project or homework for this week, which will involve a bit of application of statics and understanding materials. So with that, like I mentioned, thanks to everyone who submitted like a project. I did try to look at those before the class. And like I said, it did make me realize that maybe there's some things that might be worth explaining or going through together. And so to begin, I'll just start off by talking about some of the concepts that we did before. It's always good to, even if you've seen these before or have heard them before, it's good to just have some spaced repetition when you learn about these new concepts, because they're not usually the most like intuitive or familiar. It's just good to have a repeated exposure to the concepts. So to begin, we'll talk about a force. Like I said, a force is some kind of pushing or pulling influence that can cause an object to move. So in classical mechanics, whenever you have an object that's in motion, that's accelerating, then there is some kind of force involved. And even if you don't have some kind of motion, there can still be forces involved. Forces are a very fundamental part of how we describe how we think about motion. So that's force. Keep in mind it is a vector quantity, so you do have to specify a direction when you're talking about force. So it's not too meaningful to say that the force is 10 newtons, but you also need to say that the force is directed maybe upwards, maybe 15 degrees to the left. Whatever system you're using to specify direction, you do need to specify direction when it comes to force. And I'm getting a bit of feedback here. If you're unmuted in the Zoom call, I'd recommend muting. I don't know if you can also hear that, but sorry about that. The units for force are what we call newtons, and this is just the standard like metric unit for it. You can split it up kind of into this kilogram times meter per second. And in the imperial system, we have something called the pound force. More often you'll hear it called the pound, but that's a bit ambiguous since pound can technically refer to both a mass and a weight. So there you go, that's force again. And this is something else that I brought up, maybe I didn't call it this, but when it comes to force, there are these things called Newton's laws of motion. There's 3 of them, and the only one that I'll really talk about here is Newton's second law. And this one very tersely, very concisely can be stated as F equals ma. And you might have heard this before, you might have done this in your classes, but the more precise statement perhaps is the sum of all external forces, that's this sigma sign, sum of F, is equal to mass times acceleration. And just again, to reiterate, these bolded quantities mean that they're vectors. So forces are vectors, acceleration is a vector. And so whenever you're considering any object, whether it's the laptop in front of you, the sum of all external forces that act on that object. For example, there's gravity, there's normal force that the table has on the laptop to support it. All of these are adding up to 0 because your laptop is not accelerating. It's just sitting there in front of you with 0 acceleration. And that's kind of the power of Newton's second law, where it allows you to, given that you understand the motion of an object, you can kind of understand the effect of the forces that are acting on it. So like we've done before, I'll just give you a couple quick examples. I won't have as many of these this week as I did last week, but just to start us off, here are 2 quick questions to get you thinking. First one, you're just watching a ball in free fall. It's a classic physics lab experiment. You drop a ball and you have some kind of instrument, maybe a rangefinder, or you're taking a slow motion video, and you observe that it's accelerating 10 meters per second downwards. You also know that the mass of the ball is 5 kilograms. And so what can you conclude? What is the net force that acts on the ball? I guess if you're in the Zoom call, you can answer in the chat, either as a public or private message to me. I guess if there's some, I guess that's probably the best way to do it, since there are, I guess, a lot of students. And whenever you do submit these, I do want to see the units. And since it is a vector quantity, also a direction. For the direction, you don't have to worry about vectors. You can just say like upward, downward. Yeah, I've received a couple answers. Seems like you have the idea where you can just multiply the 2 quantities, F equals ma. You've observed the acceleration, which is 10 meters per second. You know the mass, and so that makes up the right-hand side of this equation. Sorry, if you're in the Zoom call, would you mind muting yourself? Nothing personal, it's just, at least for me, I get a bit of feedback, audio feedback, so. Yeah, hopefully that's good. All right, so that's the first one. As for second one, let's see. This one's a bit. So now we have our second scenario where you're observing your robot. You're very familiar with this thing. You weighed it. You know that it weighs. Well, based on its weight, you know that its mass is 10 kilograms. And so you're driving this thing forward in a straight line. It has a constant acceleration of 2 meters per second. Maybe you're using a rangefinder again to determine this. And based on that, what can you say about the net force that acts on this robot? Remember, I want a unit and a direction, as well as the number. So I see a couple answers. One person says 20 newtons forward, which is correct. You can use the same kind of reasoning where you know the acceleration and you know the mass. And just given these two quantities, by Newton's second law, you know everything you need to know about the net external force acting on the object. Now, I see also someone put an answer where they say 20 newtons forward and 10 newtons down. And this is pretty interesting because if we think about the previous example where the ball was in free fall, we had that kind of gravitational component that was an external force, a net external force acting on the ball. And although I didn't say it explicitly, in this scenario, of course, we have gravity because we're on Earth. Maybe that's the assumption there, which is true. And this kind of brings up the importance of considering what we mean by a net external force. And so it's completely true that gravity is acting on the robot, but in this case, the gravity is not causing the gravity does not consist of, I guess, the net external force, right? The net external force is kind of determined purely by the acceleration, where if we think about this whole system, sure, gravity is acting on the robot, but the floor is also acting on the robot to keep it from falling. And so you have these two forces, one directed downwards, which is the weight of the robot, and you also have one directed upwards, which is the floor pushing against the wheels of the robot. So the net external force due to gravity, even though those forces are present, they are acting on the robot. Their net effect is zero because they kind of cancel each other out. They happen to have the same magnitude and opposite directions. So because the robot is not accelerating downwards, there's actually no net external force downwards. And we can conclude that simply purely by looking at the motion of the robot. So that is a good thought to consider the gravity, but this kind of illustrates that in this case, you just have to think about the acceleration. So that's that. Hopefully that's a good refresher on force. We'll be coming back to this topic shortly towards the second half of the class when we talk about statics and how to design things that are strong. We'll do a bit more of a review though, since this one's especially going to be perhaps a more foreign concept compared to force, and that is torque. It's probably a word that you've heard used before. It might also have been called moment, although moment can refer to many different things. And a torque you can think of as the rotational analog to a force, where a force is some influence that can make an object move, just move around in space. A torque is an influence that tends to make an object spin. So if you've ever seen those videos of the astronauts on the International Space Station, you can see sometimes they do demonstrations where they let objects go and they stay afloat and they don't move. If you push on one of these objects, they'll move, and that push is what we call a force. But instead of just pushing on it, if you just give it a little twist, you'll see that the object will just stay afloat in midair and it'll just spin. And so that twist, that's what we call a torque. This one is also a vector quantity, so it also has to be specified with a direction. And we don't usually call this direction, for example, like counterclockwise or clockwise, but we usually refer to it in the same kind of vector notation that we use for forces. So don't worry too much about vector notation if you don't know about it. Just know that in general, if you're looking at this kind of two-dimensional case, where the system is in 2D, then there's only really two directions. One is clockwise, one is counterclockwise. And so quick question for you, I guess the hint is that you have this right-hand rule. Is this little arrow spinning in the counterclockwise direction positive or negative? That is, does it have the positive sense or the negative sense based on the right-hand rule? If you forgot it, that's okay. I'll tell you the answer in a second, but also give you a moment to answer if you remember. Remember that the rule is you kind of curl your fingers in the direction of the spin and the thumb points in the direction. So out towards you is positive, into the page is negative. Yeah, someone says positive, and if you take your hand and you curl your fingers in the direction of that arrow, you'll see that your thumb is pointing towards you, which means it's the positive sense. And the unit for this, we have the Newton meter. In imperial, we have the inch pound or the foot pound, which is just 1 inch times a pound of force, or a foot times a pound of force. So there you go. To give you a chance to think about what torque is a bit more, consider here this problem where you're trying to turn one of these Torx screws. If you know what I'm talking about, they're the screws where the head is kind of like a star-shaped pattern. And so there are different tools that you can use to turn these screws. One of them is a screwdriver, and one of them is this kind of Torx key, kind of like an Allen key, but instead of an hexagon, it's that star shape. And the key refers to like that L-shaped shape in the bottom right here. So let's say that I'm working with these screws, and I know that I need to apply 10 inch-pounds of torque to a screwdriver to turn the screw. So given that fact, I also have a Torx key where the handle, this horizontal part, is 4 inches long. How much force do I need to apply to the end of it to turn the screw? And that little arrow there, we're pushing kind of into the page. It's perpendicular to the handle of that key. So instead of twisting, I'm applying a linear force to the key to try to turn the screw. So I'll wait for just one more answer. All right, and so I guess to go through this one, what you might recall from the previous week is we have this expression for torque, which is like R cross F, or the moment arm multiplied by the force that you apply. So even if you didn't remember that, maybe through thinking about the dimensions, thinking about the units, you could kind of guess what the operation is. In this case, I suppose you're dividing the 10 inch-pounds by 4 inches. And the way you can think about this is we have a 4-inch handle, and you're applying a certain force at the end to try to turn this handle. And so the torque that you're going to get about the axis of rotation there is 4 inches times whatever force you're applying, and that needs to equal 10 inch-pounds. So you take the 10 inch-pounds, you divide it by 4, and you get 2.5 pounds of force that you need to apply at the end of that handle. So hopefully that it's a bit illustrative of what torque is. I know that when you first learn about it, torque is a bit of a strange concept since we don't talk about it too much. I see in the chat someone says they have a question for me. I guess feel free to ask in the chat, or you can speak up, I guess. Does it mean you have to divide or multiply? So in this case, the operation that we did was division. Just thinking about the units, you know that here we have inch times pound, and here we have inch. And it's asking us for a force. So using a bit of dimensional analysis, you can kind of understand that we have to divide inch times pound by inch, and we're left with pounds. So that's a good sign. The other way is to think about that equation for torque where tau is equal to r cross f, or r times f in this simple case, where you have this length of 4 inches and you multiply it by something to get 10 inch pounds. So you're dividing 10 by 4 to get the pounds. I'll give you another chance. This is a similar example where you're trying to go between force and torque. So let's say that I have a door, it's a meter wide, and in the bottom I have these diagrams where you're kind of looking top-down view onto the door. That little shape on the right is like the doorknob. So I know that to open this door, I need to push at the handle with a force of 15 newtons. So if I want to try to turn this into an automatic door, by putting a motor at the hinges, how much torque does that motor have to be able to produce in order to turn this door? And on the left here, you can see this arrow is kind of how I'd apply the force to open the door. On the right, this is what the motor would be doing, where it's applying this torque directly to the hinges of the door. I see one answer. I'll give you a few more seconds just for some more to come in. All right, someone asks about what I mean by 1 meter wide. I guess that might not be clear. I'll grant you that. I guess imagine this is the door that you'd look at in the door frame. What I mean by width is the dimension from the horizontal dimension. So from here to here. That is 1 meter. So I guess the part you'd walk through is 1 meter, as opposed to the height, which is the tall part, or the thickness, which is probably like an inch of material that the door is. Right, so I have a lot of answers at this point, and I think almost all of them are 15 Newton meters, and that's correct. The unit, I see some people question marks there. It is Newton times meter. You can call it a Newton meter. It is technically equivalent to something called a joule, but when we talk about torque, we always call it Newton meters and not joules, even though they're technically the same unit. So you can just say a Newton meter. And for the imperial system, either inch pounds or foot pounds. So it seems like you have the hang of it. A lot more of you got the second question, which is promising. And so this is kind of what we were talking about with that robot arm question from last week's project. I understand that might have been, for some of you, a bit abstract, especially since I didn't go through some of these examples, so don't worry too much about that. And from here, I'll have a brief detour as I talk about some other important concepts in mechanics, and this will tie back into our discussion last week about motors. And so in physics, in mechanics, we have this concept called work. And in our colloquial usage of the word work in conversation, it kind of indicates what it really means. So I might say like, oh, I work at this company, I work from 9 to 5. That means you're doing something, right? It means you're, maybe if you work in construction, you're carrying things around, you're moving objects around. And so when it comes to physics, what we mean when we say work is whatever happens when we move an object using a force. So that's what work is. The work is what we've done when we've moved something using a force. When a force is exerted through a distance, that is work. It's a bit abstract, but to put it in terms of some like robot competition things, if the robot is pushing a ball towards a goal, maybe it's playing soccer of some kind, then the robot is performing work on the ball because the ball is being moved, and the robot is the one that's applying that force onto the ball. On the other hand, if we maybe made a mistake in programming the robot and it's driving into a wall and it's just fruitlessly continuing to drive into that wall and it's not moving because the wall isn't going to be moved by your robot. In that case, the robot is still applying a force. The robot is pushing against the wall as hard as it can, but it's not actually doing any work because the wall is not moving, the robot is not moving. It's applying this force through zero distance, and so it does no work. The unit for work is something called the joule. That's equal to a Newton times a meter. So you'll observe that that's the same unit as torque, but we call it a joule rather than a Newton meter, just because we're talking about work here. So there we have this new concept. It's called work. We're not going to do too much with work. We're just going to use it to introduce yet another concept, which is called power. And so power is also another word that we use day to day, but it has a very specific meaning when it comes to mechanics. And that meaning is the rate at which you do work. So you might hear power being referred to when people talk about motors, like how much power does that motor have? What's the horsepower of that engine? You might also see power in terms of, I guess, other situations, like you're generating power from a power plant. So what that power refers to is just the amount of work that you do over a certain amount of time. So it's kind of like a speed, except it's about work rather than distance. It's just work over time. So the unit of that, as you might imagine, is just the joule over the time unit, which is a second. So joules per second, we call that a watt. You can break that down into like the basic units if you're curious. And the imperial version is something called, I guess, foot-pounds per second. But it's also expressed in something called horsepower. So like 550 foot-pounds per second is equal to a horsepower. And apparently that measurement, maybe that has something to do with the amount of power a horse can put out. I'm sure there's a story about that somewhere, but a lot of the time you'll see engines characterized by how much horsepower they produce. So like a 10 horsepower engine, maybe on your lawnmower, your car probably has a lot more horsepower than that. But whenever you see that term used, like horsepower to describe an engine, what it's talking about is the rate that you do work. So again, we're not going to do too much about that, but I just want to contextualize this so that when you do look at something like a motor data sheet, when you're picking motors, you understand what power is referring to as opposed to torque or speed. So I've been making a kind of big deal about these units, and this is where we'll take a close look at the units of power, the dimensions of power, and we'll find something interesting here. So like I just told you, the unit of power is this Newton times a meter per second, Newton meters per second. And so here's one way to break that down. We have work, which is the Newton meter, and time, which is a second. So we have this one way to think about power, which is this force exerted through a distance and how much of that you do over a time. So that's one way to think about power. And what else you can notice is that the Newton meter is also a unit of torque. So you can break down these units a different way, which is kind of this torque multiplied by an inverse time, right? And these units should be familiar from last week when we talked a lot about angular speed and angular acceleration, where we have torque multiplied by angular speed, like radians per second, RPM, degrees per second. The actual dimensions of that is actually inverse time. It's a frequency. And we're multiplying that by torque. And so what we see is that power is also equal to torque times angular speed. It's a different way of thinking about things, but when it comes to motors, this is perhaps a more useful way to think about power. It's how much torque that engine or motor is able to generate multiplied by how fast that motor is able to spin while producing that amount of torque. So when you hear about the power of an engine, that's what it's referring to. It's the product of its torque, what kind of work it can do, and how fast it's doing that. So whenever you look closely at a motor, you're probably going to look at like the data sheet of the motor. So in that data sheet, you're almost certainly going to see a graph with a whole bunch of lines on it. And I'll pick out two of the lines from this graph that you're going to see. And that is these two. So on the left here, remember this tau symbol, the horizontal axis, that is torque. And on the vertical axis here on the left, we have omega, which is rotational speed. And here we have power. Right, and someone's asking about these graphs, and I'll get into that, I guess, right now. So let's just think about how a motor behaves for a moment here. And let's say that we have our motor and we're putting absolutely nothing on the motor. We're just running the motor fresh from the package, just a stock motor, and we're connecting it to the power supply and it spins. And right now there's no load on the motor. The motor is able to spin completely freely with nothing holding it back. It's not doing any work. It's not doing any useful work, at least. We're just spinning the shaft, basically. And if we're doing that, the motor can spin really, really fast because there's no weight on it, right? It's not really doing a lot of work, so it can spin really, really fast. And so when you have a low torque, then you have really high rotational speed on your motor. Here on the left, I see someone asking about the symbols. This is an omega, the Greek omega, which stands for rotational speed or angular speed. So you can think about it like RPM or degrees per second. That's what this symbol stands for. On the right here, the P stands for power. And so we're thinking about this graph right here on the left. So right now we're thinking about the motor producing zero torque, but it's spinning really fast because we're not putting a load on it. And at the opposite end of the spectrum, we can think about the situation where we're putting a lot of weight on the robot, on the motor, right? Let's say this motor is one of the driving motors for a robot, and we put like a really heavy book on top of the robot. So it has to do a lot of, it has a really heavy load on top of it. So the motor has to output a lot of torque in order to continue spinning, right? Just because of how much weight is placed on the robot that the motor is driving. And in that case, if we put enough weight on the robot won't be able to move anymore. The motors just aren't capable of producing enough torque to move the robot. And when that happens, the motor stalls, it stops spinning. So here, at this point in the graph, omega is zero. There's no rotation anymore, and the torque is a maximum because it's trying as hard as it can to try to turn the motor, and it's putting, that's the maximum torque that it can put out, in a sense. So these are the two situations we have, and in between that, it's kind of a straight line. Maybe that's a bit idealized, but here we go. There is a lot of points in the middle. For example, we might have like a medium amount of torque. So we just have the robot, which is a bit of a load to put on the motor, but not too much. And then it'll spin at some intermediate speed. It won't be the maximum speed that the motor is capable of spinning, but it won't be zero either. So that's what this line kind of shows. And then from there, we can kind of think about the power that the motor is producing. So when there's no load on the motor and it's just spinning as fast as it's physically possible for it to go, then it's not really producing any power because there's no load on it. It's not doing anything, it's not doing any work that we want. It's just spinning freely with nothing on it. So the power is zero when the torque is zero. And on the other hand, here, when we're at the maximum torque, but the motor can't spin because there's so much weight on the robot, so to speak, then it's also not producing any power because the robot can't move, right? And so here we see that the power is going to be maximized somewhere in the middle, where there is a medium amount of torque and medium rotational speed, where we know that based on this dimensional analysis, that power is equal to torque times the rotational speed. So just by multiplying those quantities, we kind of see intuitively why the power is going to be greatest somewhere in the middle of the minimum and maximum, like minimum and maximum torque, right? And whenever you look at a motor data sheet, you're going to see like a graph with a whole bunch of lines on it. This shows two of the lines. Other lines you might see are like the current that you have to put in. So that's going to be like a straight line going kind of the other way. You might see an efficiency line. So that's the torque you should run at if you want the maximum efficiency out of your motor. But this kind of gives you a first glance into what you should be looking for in a data sheet when you're picking out a motor. You want to make sure that for the application, you want to know how much torque you need, and you want to know what motor is going to be the most efficient at that kind of torque you need to produce. So I'll put that aside for now, and I'll go into one more review topic. This is also from last week, and that is gears. And I realized I might not have explained this as explicitly as I perhaps should have. When it comes to gears, like I said before, they change the direction of the rotation, they change the speed of the rotation, and they change the axis of rotation, right? And we talked about something called the gear ratio. That's how many times you have to turn the driving gear in order to turn the driven gear once, or some number of times. So that was that, but I didn't perhaps make the connection between that gear ratio and torque and speed. So in case you didn't realize it before now, I'll say it here. You can use gears to change the torque and the rotational speed that you get out from your motor. This is kind of what we were trying to do with the project, where we're using the motor to allow an arm to apply a certain force at the end of the arm. So we have this load torque being put on the motor, and the motor isn't strong enough to do that. So we want a kind of gear ratio to increase the torque that we get out of the motor. And it turns out that the ratio between gears for torque and rotational speed are the same as the gear ratio. I guess one of them is inverse, but the ratio is the same. So when you think about it, this hopefully makes sense. If you're increasing the torque at the output from a motor using gears, if you're increasing the torque, then you're decreasing the speed. Let me see if I have my gears. So I don't know if you can see me, but if you have these two gears, if you're driving the smaller gear to turn a bigger gear, at the axle of the bigger gear, you're going to have a slower rotational speed, but a greater torque. And you can think about that, at least for the speed, you can think about it as the circumferences of the two circles, right? You know how fast they're going to go just based on geometry of it. Makes sense that the bigger gear is going to turn slower if you drive it with a smaller gear. And what I'll claim is that it goes the opposite way for the torque, where if you drive a bigger gear with a smaller gear, you're going to get more torque out from the output. So to kind of illustrate this, here in the top left, it's a cutout view of two gears, specifically where they're contacting at the teeth. And so the force transfer between gears occurs at the teeth. The teeth is where everything happens, right? The gears turn each other because the teeth are pushing against each other. And so at any given moment, one pair of teeth is going to be pushing against each other. And so the forces that you have involved there are kind of, one's pushing up, one's pushing down. And we're only really interested in that contacting instead of teeth. So if you really think about that, what's really happening is you have two levers, right? Where the lever represents that tooth. And so if you look on the right, the diameter of the gears, the radius of the gears perhaps, represents how long that lever is that's applying the force against the other gear. So a smaller gear is a smaller lever pushing against like a longer lever. for a bigger gear. And so when you drive a gear with a certain amount of torque, here I represent that with M for moment. You're driving a gear with a certain amount of torque, then the same amount of force is going to be imparted at this contact point. But since the length of these levers is different, the amount of torque that you get at the output at point A here is going to be different based on the lengths of these levers. So if you have a longer lever or a bigger gear, you're going to get more torque at this output axis than you put in the input axis. And that's purely just that geometric relationship again. And hopefully that'll help you understand how gears are able to change the rotational speed as well as the torque that is transferred between these axes. Essentially, it's just levers that are pushing against each other. So with that, this will be the last thing before the first part of this class. I'll just present these sets of gears that you saw last week to you one more time. On the left, we have two gears. The left gear is driving in both cases. So here we have a 15-tooth gear driving a 30-tooth gear. And here we have a 25-tooth gear driving a 30-tooth gear. So if the left gear, the driving one, is turning at 10 RPM, then how fast is the right gear turning in these two cases? I'll give you a few seconds. You can put your answer in the chat and I'll come back in a moment. I see a few answers. I'll wait just another second for a few more before I talk about it. Yeah, all right, I see a lot more now. So for the case on the left, remember we're driving the left gear. So we're spinning the small gear with the motor and we're interested in how fast the big gear turns. So if you played with gears before, you'll probably have an intuition that the big gear is going to turn slower when it's driven by the small gear. And that's just because if you think about the circumference, in order for the big gear to turn one revolution, the small gear kind of has to, the circumference of the small gear kind of has to wrap around that of the big gear. So that was not the best answer. Okay, sorry, I'm distracted. Right, so in any case, what happens is the right gear will turn more slowly at 5 RPM in the case on the left because the gear ratio, we have 15 teeth to 30 teeth. And on the right, the driven gear is still larger. We have 25 teeth and 30 teeth. So in this case, the speed will be 5/6 of 10 RPM, which is some number. 50 divided by 6, so 8-ish. All right, so if you said, in either case, I guess, based on your answers, in either case, the gear on the right will be turning more slowly than the gear on the left, just because the gear on the right has more teeth. All right, and one last one before we part briefly for the intermission. It's the same setup, same gears, but this time we're thinking about the torque. So I put a motor on the gear on the left, and I know that motor is producing 10 Newton meters of torque. And so given that, what is the torque that I'm getting out from the right gear? All right, so I see a few answers. In this case, since we're going from a smaller gear to a bigger gear, at the output, we're going to have more torque than at the input. So for the case on the left, we'll have 20 Newton meters, and for the case on the right, we'll have 12. So that's it for the first part of the class. Like usual, I'll give you a break, intermission for the class, and we'll meet back at say 7:30. I see in the chat someone has a question. So NM, Newton meter, just refers to the unit. So it's 1 Newton times 1 meter. Can also be expressed as, I guess, kilograms meters squared per second squared. But NM stands for Newton meter. Right, so I'll see you all in a few minutes.
Thank you, Eugene. If you have any questions, you can talk to Eugene. You can use the private chat or just raise your hand. I'm not going to talk. I can only forgot to record, so I will just keep it running for a few minutes. In charge of the cutting in your teeth, or the better. Cutting. That's right, cutting. Okay. So let me know, yeah.
It's crushed up. So bullying fun.
All right, is everyone back?
Okay, Eugene, you can start the class. Yeah.
All right, well, welcome back everyone. Short break, but here we are. So like I hinted at last week, this week we'll be talking a bit about CAD, computer aided design. I'm guessing many of you are already familiar with it, so I'm sure, I guess I really have no idea how many of you are. So for those of you who aren't, I'll just briefly go over it. Computer aided design, abbreviated CAD, is refers to a way of modeling some kind of object, like a part or more complicated system in 3D using a computer. So the one that we're going to use is called Onshape. You can access it here at this link, cad.onshape.com, which I'll put into the chat. So if you don't have an account here, what I would suggest is make one right now. The process should be fairly straightforward. Let me log out just to show you what it looks like. If you go to cad.onshape.com, you'll see in the bottom right here, if you don't have an account, it'll ask you to sign up. You can press the sign up, and if you scroll down a bit, you can request an education account, which is free for students. And since you're all students, I presume you should all be able to create your account. So do go through that. I'll just show the basics of how to get started in Onshape and how you can make a simple model. The project or homework for this week will involve using Onshape to produce a model. So I'll just give you the basics, enough that you would need to be able to do what you would need to do. So if you have your account, you'll sign in. Yeah, someone's asking me about if you already learned Onshape. Yeah, don't worry about it. I'm not going to spend too much time on this tutorial. Just follow along. So the way you get started, if you have your Onshape account, yeah. So if you've never used it, in the top left corner, you're going to have this button called Create. And if you click on that, the first option is called like Document. So you click on that and you'll create something called the document. And once here, it'll take you to this 3D workspace. And the only thing that you're really going to need is two tools. The first one is called Sketch and the second one is called Extrude. So the Sketch tool is the basis for how you make things. And the way it works, you click the Sketch button, you select a plane, which just refers to one of these three planes that are already there, the front, right, or the top. I'll click on the front, and that puts me in my sketch. So you can see here the top bar of tools has changed, and I'm able to do things like draw lines, draw rectangles, and the like. So start very simply. I'll create a rectangle. By default, it'll be something called the corner rectangle. So I click on that tool. I can click and drag to make my shape. And then I need to tell Onshape how big this thing should be. And I'll do that using what's called the dimension tool. It's on this far right here. I'll click on that. And if I click then on one of the lengths of the sides, I can assign a number just by typing it in. And that gives me a 2" by 2" square. And I know it's inches because that's the unit that I specified by default. It'd also say like 2 in here, which stands for inch. And so that's how I create, say, a 2" square. And it's really the most complicated thing that you'll need to do. So I do that, I click the green check mark to finalize the sketch. And you can see now that that square that I drew is part of my workspace. From here, how do I turn this into a 3-dimensional object? There's this tool called Extrude. It's the very first one right next to the sketch button. If I click on that, it brings up this window and it asks me first to select a face or sketch region. So to do that, I just click on that square that I just drew and I can determine how long this thing is going to be just by typing in a number here. So let's say 18 inches. And now I get this long rectangular prism. So that's the essence of 3D modeling using Onshape. There's, of course, a lot more that you can do with it, but for the purpose of the project this week, this is pretty much all you need to know how to do. I'll show you one more thing, which you probably will want to use, which is the ability to create more sketches. So you can press the sketch button again when you're in this 3D workspace. And for your sketch plane, you can just click on any of the faces of this object that you already have. For example, this one. And from here, it takes me back to my sketch tools, and I can draw whatever I want on this beam again. So let's say I draw these two circles. I'm just going to leave it like that. And I'll use my extrude feature again and click on these two circles. But the other thing that I can do, instead of just adding material, if I click on this third tab here, in this little bar of the extrude window, you can see that I can remove material. And if I do that, I just drag this arrow all the way through, you can see that what it does is create a hole in that beam that I just drew. Someone's asking me if they should be following along. Don't worry about following along. Just make sure, I guess, that you can use Onshape. I'm just showing what you could theoretically be doing in Onshape. So as simply as that, with 2 sketches and 2 extrusions, I've created this beam that has 2 holes in it. So that's really all you need to be able to do the project this week. If you know how to do more, that's great, but this is really all you need to know how to do. If that was too fast for you, just worry about making your Onshape account. And if you look up online, there's plenty of tutorials and videos on how to use Onshape to this level. So you can always try to do that. If you have any specific questions later, I can also take Onshape questions like at the end of the class. But that was a very short demonstration of how a 3D CAD package can work. And I guess one more thing, now that you have this model, how can you, for example, submit it to me on Google Classroom? Well, if you look at the bottom here, you have your tabs. Right now, I'm working in Part Studio 1. That's this tab right here. And so if I right-click on this tab, you can see I have this dialog box that comes up. I'm not sure what it's called, dialog. I have these options that come up. And the very bottom one is called export. So again, I have my 3D model that I just made. If I go to this bottom tab and I right-click on the tab, it lets me export. So I click that, this new window comes up. The file name, I can name it, I don't know, my part demonstration. For the format, this is kind of important. I want you to choose the step file, STEP. It's in the drop-down menu, third one down, I guess. Make it a step file rather than say an STL or something. And that's just going to make it easier later on for me. And you can download that. And when you do that, it'll take a moment, but it'll prompt you to download the file just like it would if you were downloading any other file from the internet. So you can save it somewhere to one of your directories. And later on in Google Classroom, you can upload that step file where I'll be able to look at it. So that was an extremely fast crash course in how to use Onshape. I have faith that most of you are able to figure that out. And with that, I know that's a bit of a rush. I'll give you a few seconds to get back to what we're doing. But for the rest of the class, I'm going to try to introduce the project by talking about kind of the concepts behind what's happening in this final, I guess, third project that we're doing. So we've talked so far about kinematics, which was kind of understanding motion by describing it with mathematics. Then we talked about dynamics, which was kind of the study of what causes motion. This is when we talked about forces or torques. That refers to dynamics because we're interested in moving things. And now we have kind of another branch of kind of mechanics, which is called statics, which is the study of systems that have zero acceleration. This can mean things that aren't moving. The laptop in front of you that's sitting on your desk, that's a static system because it's not doing anything, it's not moving. And it can also refer to things that have like a constant velocity, since those also have zero acceleration. And what's really special about the property of having zero acceleration is that when we go back to our Newton's second law, when we go back to our F equals ma, the ma part is equal to 0 because the acceleration is 0. So what we're really saying about our system is that the sum of all external forces is 0. This also applies to torques or moments. And we can say that the sum of all external moments or torques is also 0. And so there's no tendency at all for the system that we're talking about to rotate or move. And this is actually surprisingly common. You might think that's a very specific case to look at, but in real life, a lot of our things like bridges, buildings are essentially static systems. At least to some extent, they are static because we don't want them to move, right? We don't want our bridges to be moving a lot. In general, we want them to be still, and we want all the forces that are going through that bridge to kind of balance each other out, so it doesn't fall down. And so that's kind of what we're going to be going into as we talk about statics. And so there's a whole bunch of math and a whole bunch of analysis that we're not going to talk about. Instead, I'm just going to introduce a few concepts that will lead us to this project that we're going to do. So the first one is stress. And here's another word that has a whole bunch of meanings in ordinary conversation and a very specific meaning when we talk about mechanics. And so stress refers to essentially a force per unit area, either inside or on the surface of an object. You can imagine if you take any object like your pen, if I take this pen and I apply a lot of force to it, I really try to bend this thing, we all know that the pen is going to break. And why does that happen? That's because there's going to be a lot of force going through this thing, more force than it's able to withstand. So that's kind of the concept of stress. There's lots of different kinds of stress. If I pull really hard on this pen, it's going to stretch out a bit. It's going to get longer, maybe. Pen might not be the best example, but if I pull on it, it's going to break because of something called tensile strength. The pen is in tension when I pull on it. A better example might be something like a suspension bridge, where the bridge is held up by a number of cables, and those cables are all under tension. Another type of stress is like compressive stress. If I push really hard into this pen, it's also going to break, and that'll be because of compressive stress. If you ever watched online, those like hydraulic press videos, those where they like crush an object in a hydraulic press, those are applying a compressive stress to an object. And there's a lot of other ones. There's torsion, where if I twist this pen really hard, it's going to break. There's shear stress. There's bending stress. And so there's a lot of different ways that an object can be stressed, but fundamentally all of them are referring to this concept of how much force per unit area you have going through this thing. So the unit of this is in standard, or in metric, it's called the Pascal, which is a Newton per meter squared. You might also know this as a unit of pressure, and yes, they are the same. And in the imperial system, which I'll prefer, we have something called PSI. So again, this is also a unit of pressure. You might have heard about how much PSI of pressure goes into your tires in like a car, but it's also a unit of stress. And since usually stress is a really big number in terms of PSI, we also have something called KSI, which is 1000 PSI. So whenever I talk about like others, like 36 KSI, I'm talking about 36,000 PSI, or pounds per square inch. And when I refer to stress in like an equation or a graph, I'll probably express it in terms of the symbol here, which is the Greek letter sigma. So sigma for stress, it's a unit. The unit is equivalent to pressure, and it's just talking about how much force per unit area you have going through the object you're interested in. And this is pretty relevant too when you're designing a robot, because the robot's also going to be under stress no matter what it's doing, right? For example, if you put a really heavy load on the robot, maybe you built the frame of the robot and it's supported on these axles, on these wheels, maybe then you put a really heavy battery on top to power the robot. If the battery is too heavy, there's going to be a ton of stress going through the axles, and that might cause the axles to break. And so understanding statics, understanding these mechanics of materials is going to help you design a robot that doesn't break even when it's put under a lot of stress, as long as you know kind of the loads that you expect the robot to go through. So that's the first concept, stress. And the other really important one is called strain. And this one, perhaps you haven't heard of as much before, but strain refers to how much an object deforms when you do something to it. So this is a relative quantity. It talks about how much change in the length of an object you might see compared to its total length. And so because of that, it has no units. It's dimensionless. It's purely a ratio or a proportion. And so we might just refer to strain as like maybe a percent or some number like 0.01. And a good way to think about this might be like a spring, like a pen spring, a coil of wire. So if you apply some stress to a spring by pulling it apart, the spring is going to get a bit longer. And the amount that it gets longer compared to the original length of the spring, that's the strain that the spring experiences. So strain is a useful quantity just because it can tell us how things will deform when they're put under stress, or also under things like temperature change, which can also cause things to deform due to like thermal expansion or contraction. And to put this into a bit of context, for example, let's consider that example where we have our robot frame that we just built. It has these axles, it's sitting on its wheels, and then we put a really heavy battery on top of the robot. If that battery is too heavy, then the axles of the robot might actually deform where they get longer because of the load that's been placed on top of them. Another example is maybe in a suspension bridge, we have our cables, and the cables are definitely going to get longer when we put a really heavy load onto them just because of the stress that's going through them, right? That force actually pulls the material itself so that it becomes longer. And the symbol for strain is this letter epsilon, another Greek letter, looks like that. When we use it in an equation or graph, it's probably going to be represented like that. And so now we have our two concepts, stress and strain. Recall that stress is kind of how much force per unit area is being put on this object, and the strain is how much it's deforming. And given these two quantities, we can kind of develop some interesting knowledge about different materials. And we have something called a stress strain curve that looks something like what I drew here on the slide. And the way that we obtain something like this is we take a sample of our material and we have a machine that will apply a stress to this sample. So maybe we have a bit of steel, and we take the steel in this machine and we just pull it apart. And as we're pulling it apart, we keep track of how much force we're applying to the sample. And we also measure how much change in length the sample experiences because we're pulling on it. And keep in mind, these are things like metals, like steels or aluminums. And we keep track of these two quantities and we just create a plot as we continue to increase the stress. We look at how much the strain changes, right? And so at the very beginning, when we just start with the material and we apply a small amount of stress, the strain, the length changes is actually linear with respect to the stress. We have this initial region here, which looks like a straight line, where if you put a certain amount of stress on it, the strain, the amount of length change you get is directly proportional to that. And while you're in this region, we call this the elastic region. The material actually behaves exactly like an ideal spring. You might not think of materials like steel or aluminum to be springy, but before we actually put them to what we call the yield stress or the yield strength, they actually behave like a spring. So if you push on them, they'll compress a little bit. If you pull on them, they'll expand a little bit, just like a spring. And if you let go of them, they'll just spring back into their original size. So that's what happens in this first linear region here. And then this point here where it stops being linear and it turns into kind of this curve here, that stress value is what we call yield strength. So the name kind of speaks for itself. That's the strength the material has, or I guess the stress that you need to put the material through before it yields, before it stops being elastic and then it becomes a plastic, right? You can imagine that if you pull on a steel bar so much that it gains like a whole inch of deformation, and it's visibly starting to deform, then it's not going to just spring back into its original shape anymore because we've exceeded the yield strength. We've entered this plastic region where now we've permanently deformed the material. And so how is this relevant to designing a robot, for example? Our goal when we design something is for the part to always stay in the elastic region. We're okay in general if the part is a little bit deformed under a load. In fact, we expect that. It's impossible for it not to have a tiny bit of deformation. And that's okay as long as we stay in the elastic region, since once we remove the load, it's going to spring back to whatever it originally was. However, if the part experiences such a strong loading that it's permanently deformed, then the robot has failed, right? The part has failed. It'll no longer spring back into its original shape. And that is what we want to avoid here. So when we're designing something, we kind of want to predict the loads that the system will experience. For example, let's say I'm in charge of designing the axles for the wheels, and I have an idea of how much forces and where the forces are going to be. I want to make sure that I design the axle of the correct material. I want it to be thick enough that it will withstand whatever loads are put on it without experiencing this kind of permanent deformation, without exceeding its yield strength. And so things like the yield strength of a material are determined by its material properties. So you can look these up in like tables, or you can just look it up online, like what's the yield strength of this alloy of aluminum, of this alloy of steel. Even for other materials like plastics, you can probably find tables where they provide the yield strength. And you want to make sure that when you're designing something out of this material, you want to make sure that the geometry of the material is such that in the use case that you're using it for, it's not going to yield. And in fact, we want to do a little bit better than that. Not only do we not want the components to yield, in most cases, we don't even want it to come close to yielding, because when we're predicting how much load it's going to see, there's no way for us to know exactly, since we can't see the future. We might think that the greatest load that this robot is going to see is like a 10-pound battery, but maybe then suddenly someone drops the robot and it's seeing a lot more load than that. Or someone drops the battery on top of the robot and suddenly it's seeing like an impulse, which causes a force of like 20 pounds. And so we want to have a bit of factor of safety when we design things. And you've probably heard this term before. It's a safety factor or a factor of safety. And that's just some number that tells us how much more or how much less than the yield strength that we expect the worst case to be. In other words, we have this kind of equation here where you can calculate the safety factor by dividing the yield strength of the material by the maximum expected stress that you expect the material to, or the component to see. So if you predict that your axle is only going to see 1 KSI, and you know that the yield strength is 3 KSI for whatever material you're making it out of, then you have a safety factor of 3. That means that you can have a load, you could have an actual load case that's 3 times what you actually expect it to be, and it'll still be okay. You won't yield because you have that safety factor of 3 built into it. So that's all good. And that's going to bring the question, it's going to raise the question, how do we determine what's the maximum expectation of the stress we're going to see? And the real answer to that is we can't know, but in practice, there's a lot of things that you can do to get a really good estimate of what's going to happen. So when you're designing a robot, you probably know what you're going to do with the robot. For example, if you're in charge of designing the arm, you know how heavy a load that arm is going to have to lift. You know what that arm is going to be attached to. So you have a really good idea of the forces and torques that are being applied to the various parts of that arm. And because of that, you're able to actually calculate what the maximum stress is going to be. Now, this kind of brings us to what the project is going to be. We're going to try to design a robot arm that is able to withstand a certain amount of force while still being lightweight. The way that I'm going to analyze this is using a tool called finite element analysis. And this refers to like a computer software or program that represents a 3D model, something that you might create in Onshape in CAD. And it represents that model as a mesh of thousands, if not hundreds of thousands of tiny elements. And what it does, it'll solve these equations for stress and strain for every single node in that mesh. And since it's a computer, it's able to do these things very quickly, and it can tell you the equivalent stress and the deformation that this part will experience given the conditions that the user puts in. So I guess to give you a visual example, this is an example of how a finite element software might treat a beam bending problem, where we have this 3D model of a beam. It's like a rectangular prism. And the load case that we're applying to it is we're holding this end of it fixed, and then we're applying a force straight up on the other end. So we're trying to bend this beam upward in a sense. And what the software is able to do is calculate the stress at each point on this beam based on this loading condition. So as I introduce this project, there will be one more thing that I want to talk about, and that's specifically this beam bending problem. When it comes to a robot arm, the robot arm is usually this like long, rigid member, kind of like your actual arm, where it's supporting a weight at one end and it's kind of being driven by a motor at the other end. And what's going to happen is you have this beam, this arm that essentially has a moment being applied at one end, and that's going to cause various stresses and deformations within that beam, within that arm. So when it comes to designing something like a robot arm, which is essentially a beam, you kind of have this cantilever type of problem where you have your 3D part, which is this beam, and you have a force that you're applying to the end of it. So think of a diving board. The diving board is held fixed at one end, and at the other end, you kind of have a person standing on it, which is the load. And it's essentially what's happening with your robot arm. You can think of the robot arm as a diving board where it's being held fixed at one end by a motor, and at the other end, there's a load, like you're trying to pick up a heavy object with the arm. And so that entire member, that entire arm itself is going to be put under stress because of this condition, right? And the objective is to design this part of the arm so that it's strong enough to actually withstand these conditions and not break. So just based on your intuition, consider these two beams here. One of them is kind of this upright position where you're pushing into kind of the long end of the board. And hopefully from your intuition, you can imagine that that's a very strong way to have a beam. On the other hand, we have this kind of diving board formation where you're kind of pushing down on the flat end. And hopefully from your experience with diving board, you know that it's not very strong in that formation where the board is able to bend and flex easily just because it's not as stiff to this direction of loading. So these are things that you should consider when you're designing something. From here, I'll just go straight into introducing the project. And it's going to be a bit of a long-winded introduction, but for next week, your task, your objective is to design and model a rigid arm member for a robot. So It's going to be pretty simple for the design itself. You don't have to actually design a whole assembly, but just a single member. And your objective is to create the lightest weight design that still meets all of the requirements. So you want to make it as small in volume as possible, essentially. So what you'll be submitting are step files of what you create in Onshape, and I'll run the computer software analysis on what you submit, and I'll show you the results next class, so you can get an idea of how your design performs under this loading situation. I do, for this week, want you to submit it a bit earlier, by Thursday, just so I have time to download all of the submissions and run the program. So it'll not be analyzed if it's late or if it doesn't meet the requirements. And for the requirements, I'll get into that now. It's pretty basic. It doesn't have to be anything too complicated. It just needs to be something with 2 square ends, so 2 inches by 2 inches square ends, and they need to be 18 inches apart. This might be a bit abstract, but I have a picture on the next slide. I want the whole arm to fit inside of a 2 foot by 3 inch by 3 inch bounding box. So nothing crazy big. It should just be reasonably sized given the constraints for the ends of the arm. And I want you to just have a single body. So no assemblies, no multi-body parts. Just make a single body in Onshape, export it as a step file, and submit it. To hopefully illustrate what I mean when I'm talking about this arm, you're not trying to design like a whole, actual functioning arm with servos and joints and gears and all that. All I want is that single rigid arm. Think of it like the bone of the robot, where you're just designing this stiff structural member that's going to support whatever else is attached to the arm. So the simplest design that's going to meet all the requirements is this here on the slide. It has 2 2-inch by 2-inch square faces on the ends, and it's 18 inches apart. So it's essentially just an 18-inch by 2-inch by 2-inch rectangular prism, and this meets all the requirements. It has the 2 faces that I asked for. It fits within the bounding box, and it's a single part. So you could just submit this, and that's it. But you probably won't win in terms of how light it is, since this isn't the lightest possible design that you can make. In terms of additional requirements, so to speak, the load case for this arm is that it's going to support 250 pounds in this cantilever setup. So it's going to be essentially the same as this setup, where one end is fixed and the force is applied directly to the other end. So it's kind of this situation where I'm holding one end of the arm, like I'm holding this pen, and a force is being applied to the other end. So it's trying to bend this bone of the robot. And you're just trying to make it strong enough to withstand this 250-pound weight, right? The material of the arm is going to be steel. Don't worry about that when you're CADing. That's just the setting that I'm going to set. But what that means for you is that the yield strength is going to be 36 KSI, 36,000 PSI. But you'll need a safety factor of 4, which means the maximum permitted stress that you're allowed to have is 9 KSI. To give you an example, I know for sure that I do not have a great intuition for how strong a 18-inch steel beam is going to be. Let's say that you submitted this simplest possible design, which is just this rectangular prism. If you do that, then this is what happens when you run it through the simulation, where the maximum stress is 3.4 KSI. You can see also in the model what kind of deformation occurs. We have, if you look at my pen in the camera, if I'm holding the pen at one end and I apply the force straight down on the other end, it's going to bend a bit. It's going to bend in the shape that you see on the slide here, where you have a bit of beam bending due to the weight on the other end. And so you can see here that we have a huge factor of safety. A requirement with safety factor of 4 is only 9 KSI, and we're already here at 3.4 KSI. So we're well within it. this one passes. It's way stronger than it needs to be. So there's a lot of room here where you could try to save some weight, right? And so let's see another example. Let's say you design something like this, where you take away some material from the top and bottom, getting this kind of like dog bone shape. If I reduce the thickness of this beam, then the arm actually fails. It fails to meet my safety factor of safety, where you can see from the result here that I get 11.7 KSI, which does not meet the requirement of 9 KSI. So I made the robot arm too thin here. So if I actually designed this and I made this, then the robot arm would not pass my requirements. There's a chance that it might fail. And so your task is to design in CAD, in Onshape, some geometry for an arm that meets these constraints and is as lightweight as possible. It's the smallest volume as possible, while still being able to meet the criteria of having a maximum stress of 9 KSI. And so now what you're probably wondering is, how can I know that? I don't have access to the software, so how do I know how much stress is going to be going through my beam? And so the answer to that is you might have to do a bit of math. When it comes to stress due to beam bending, we have this equation here. M times y divided by I is the maximum stress that you're going to get. So I'll simplify this a lot just by taking out some of the calculations you have to do. In our case, the value of M is 4,500 inch-pounds. And the way that I get that is just multiplying the length of the beam times the force that I'm applying at the end. This value for y refers to kind of the distance from the neutral axis to the top or bottom of the beam. You don't have to worry too much about this. As long as you make a design that's symmetric from the top to the bottom, then the neutral axis is just the center. So it's half the height of your beam. So for example, just take a look at this cross-section here on the right. If I design something like this beam, the simplest possible one, where the cross-section is 2 inches by 2 inches, then the neutral axis is just the center. So my value for y is just half of 2 inches. It's 1 inch. So that's that. And finally, this quantity called I, which refers to the moment of inertia. It sounds a bit complicated, but all you have to know is that the value of I for a rectangle is equal to the base times the height cubed divided by 12. So if you have a rectangular cross section, you just take the base, the height, you cube the height, you multiply them together, and they divide by 12. So for example, if I were designing this shape, what I would do is I'd just take the smallest cross section here, which is this rectangle. I take the length of the base, which is 2 inches. I take the height, which I think is 1 inch. I'd cube that and divide by 12, and I get this value for I, which is enough for me to calculate the maximum stress or estimate it. Now let's say that you're interested in having more complicated shapes. If you're really motivated and you want to have this really complex geometry, I'd urge you to try to learn how to calculate the moment of inertia for yourself. If you're interested in some kind of standard shape, for example, if you're interested in I-beams, for example, an I-beam refers to a metal beam used in construction that looks something like this. And these are known to be very strong in a certain direction. If you design something like an I-beam, you actually have a great advantage, which is that there are tons of tables out there that tell you the moment of inertia, this value of I. They just tell you what the moment of inertia is for the various I-beams. So I guess the first result I get is some calculator. So if you design a cross section like this, you can just, I guess you can have this calculate the value of I for you. There are also tables out there that are used, but you have a lot of options there. So that's something you can do. Also, I would say, I'd urge you to, if this is all too overwhelming, just don't worry too much about trying to optimize it. Just try making some creative shapes and on shape. Don't worry too much about the math. And as long as you submit it on time, I'll analyze it, and you can see next week how that shape performs, which can help give you an intuition of how this beam bending stuff works. I see someone has a hand raised. Feel free to ask your question. I guess you can speak up or type it. Do you have a question, Christopher? I'm not sure if you're asking the question. I can't actually hear anything, but feel free to type it in the chat if you're on the Zoom call. I mean, you are on the Zoom call.
Did you hear that? Did you hear the question? Did you hear the question, Eugene?
Or I can't hear anything. I guess I
Okay.
can't hear anything.
Okay, so for the second bullet, you see that says in our case, M is approximately 18 times 25 feet. Wait, does it have to do with like a measuring stuff or like a measuring the shape?
Oh, so in our case, so in the most general case, M is like a function based on various factors, but the case that I set up is pretty simple, where we're just putting a 250-pound weight on the other end of the cantilever, and the other end is fixed. So in this case, the maximum value of M is going to just be R times F, or like 18 inches, which is the length of this beam. Yeah, that's 18 inches apart, so that's where the 18 comes from, and then multiplying that by the weight that we're applying. So that gives us a maximum internal moment for the beam of this value of 4,500. So you can just use that in your calculation. Technically, I guess due to the 3D geometry, it's not completely perhaps accurate, but as I'll show in the next slide, it does give a fairly good estimate for simple geometry. Yeah, so I guess I'll just go into the example. So here I'm analyzing the simplest example, which is just this 2-inch by 2-inch by 18-inch arm. If I design something like that and I'm interested in predicting how much stress I'm going to get, I start with this value 4,500, and I have this geometry. So the cross section of my beam is just this square that's 2 inches tall and 2 inches wide. And because it's symmetric, I know the neutral axis just goes straight through the middle. So in this case, my value of y, my distance from the neutral axis to the top, is 1 inch. And my value for I, since it's a rectangle, is b times h cubed divided by 12. In other words, 2 times 2 cubed, which is 16, divided by 12. And so my moment of inertia is 1.3 inches to the fourth. And so given this, I put this into my equation, my over I, and I have 4,500 inch-pounds times 1 inch, that's y, divided by I, which is 1.33. And that gives me 3,300 PSI, which is 3.3 KSI. And if I go back to my simulation, this tells me here that the maximum stress is actually, might be hard to read, but it says 3,383 PSI. So pretty close. Not quite the same just because of like the finite element simulation and this idealized model, but you can see that you can predict fairly reasonably for simple geometry what the simulation results will be. And the advantage of the simulation is that you can actually put in more complex geometry than you know how to analyze. For example, if I design something like this, which saves weight by putting holes in the beam, I have no idea how to analyze this mathematically, but I can get a fairly good estimate, and then the simulation will tell me the details of where the max stress occurs, what the max stress value is, things like that. And so what I want to emphasize here, I guess I haven't really made that clear. I don't want you to worry too much about like figuring out the exact prediction of meeting the stress and things like that. I do want you to try things that you think are good, you think might be a good way to save weight on like a robot arm. For example, you might think that putting these holes is a good way to save weight, and it might be, as long as it doesn't cause the stress to exceed our kind of requirement of 9 KSI. So yeah, I do want you to try to be creative. In summary, what I want you to do for the project is to go into Onshape, create a model of the arm that meets these requirements. And the only requirements is that it has these like square faces at the ends, and it's 18 inches long, right? And it's not too big. So that's all you have to do. Just go into Onshape. You could just make something like this and make some slight modifications, right? Nothing too complicated there. And the secondary goal is just to make the arm as light as possible. You want to remove as much material. You want it to be as small in volume as possible. There's a lot of ways you can do that. You can try something like this, where you shave away the thickness of the arm. You can try putting holes in it like this. There's really a lot you can do in terms of weight saving techniques. And this is pretty good for design because you want a lightweight robot because it will make your robot faster, essentially. You have less weight, all the better. So this one's, I guess, kind of optional. If you really want to try to like min-max this, to optimize this, you can try going for these calculations where which is a good way to kind of get an estimate of how much stress you're going to get, assuming you have a simple enough geometry. But mostly, I want to emphasize, just try being creative. I'm going to run the simulations if you submit them on time. So you're going to next week how your design performs, and that's really the main goal here. So in conclusion, just make this model, submit the step file to Google Classroom by Thursday, and next week we'll see how you guys do. And that's pretty much all I have for next week. Just work on your project and submit this to Google Classroom by Thursday, and I'll see you again in the following week. Let me know if you have any questions about the project or any of the things that we talked about. But other than that, I'm done for the day.
Any questions? I have a question. When is the homework due?
I guess I'll mention, if you're interested in running these yourself, what I'd recommend is, I guess I'm not sure if there is too many free software out there for doing FEA, but if your school has a license for something like SolidWorks or like Fusion 360, these softwares have like built-in packages for running FEA, other softwares like ANSYS or Console. So if you're really interested, I'd recommend asking your school. If you're in high school especially, there's a chance that maybe your like tech department has a license for it. The other option is something called Fusion 360, where I think you get a limited number of like these free cloud points that you can use to run simulations on the cloud. But I don't know too much about that. You might need like a special education license for it. So unfortunately, I don't know of any like really easy to access free software for FEA, but as you go through school and like higher education, you're definitely going to have access to these softwares. So as you go through mechanical design, it's a good skill to pick up, especially like estimating things with hand calculations. yeah, so with that, I'm actually done. You can work on your projects, I guess, or ask any questions.
So remember, who has to address it? After that, then we have a special class. Very study is very convenient. No competition. One class. All the reading, all because we are already suggesting that and we want to read all that. Please stop recording here.